So this is the third service provided by, the internet protocol. So routing, as it is called, is the discovery of the path, and it's also called control plane operations. Okay, so in future, if somebody says control plane, data plane in the networks, you should be able to start thinking about them in more meaningful fashion. Okay.
Okay.
And there are three main algorithms used in the internet for routing: the distance vector or the Bellman-Ford algorithm. The link state algorithm uses the Dijkstra shortest path algorithm. And then you have what is called as path vector algorithm. Okay. I didn't actually, I think now if we actually go and see the first chapter slides of Kuros and Ross, it would actually make sense. So I don't have the picture here, so maybe I can postpone the discussion about the routing infrastructure. But essentially, you have our university, which is a large, organization, and there is one router which basically takes us out of the university into the rest of the world. So such a router is called as an enterprise router. Okay. It connects to the router in the internet service provider on the other side. And such a such a router is called an edge router. Okay. The edge router connects to a core router, and the core routers, actually do the routing in the heart of the internet. They're connected in almost a mesh topology, so that there are a lot of alternate paths, and also reliability is maintained even if one path goes down. And then you go from the core routers to the edge router on the other side, and from that edge router to the enterprise router on the other side, and finally into the the host that you are trying to talk. Now, when we talk about hosts from home, then we actually connect to what are called as access networks. Okay. And then the access networks talk to the edge networks, which talk to the core networks, and so on. So there is that sort of hierarchy in the routing infrastructure. And every internet service provider is basically a single administrative zone. Such administrative zones are called autonomous systems in networking terminology. Okay. And so you have protocols which work within a single autonomous system. And the distance vector algorithm and the link state algorithm are examples of algorithms which are implemented in a single autonomous system. The protocols corresponding to them are routing information protocol, which is the distance vector algorithm, and the open shortest path first algorithm protocol, which is basically using the link state algorithm. So RIP and OSPF are protocols which work within a single autonomous system. If you want to go from one autonomous system to the other, then you have to use the border gateway protocol, BGP, which uses the path vector algorithm. Okay. So BGP is very complex. In fact, the link state algorithm is not so complex, but the OSPF protocol is quite complex, because even an autonomous system is very huge. You have a lot of networks in a single autonomous system. You have a lot of routers in a single autonomous system. So they do a lot of, hierarchical division again within an autonomous system also. I'm going to leave it to you to just go through Kameshwari's video for the link state. I think that's a much better thing than me talking about it. On the other hand, I find the Bellman-Ford algorithm is explained as it is done in algorithms, but in networks, it's a little different the way it operates. So I thought, I'll talk about the distance vector algorithm. This was the first algorithm implemented in routers in the world, right? And it's part of the Unix operating system. And, therefore it became quite popular, but it doesn't work too well. We'll see why, and why it's no longer really used in the networks today. Okay, we have already seen this, but just as a recap, I want you to again see that when we configure an IP address on the router, it creates an entry in the routing table. So we are configuring IP addresses on ETH0 and ETH1, bringing in the necessary directly connected entries in the routing table. Okay. Then when we configure the router R2, its entries are actually populated in the routing table of R2. So at this point of time, we have both the routers having entries for directly connected networks. So R1 is, knowledgeable about N0 and N1. R2 is knowledgeable about N1 and N2, but R2 is not knowledgeable about N0 and R1 doesn't know anything about N2. In the ICMP discussion and the forwarding discussion, we have said, okay, we add these entries manually using the route command. That's how the routers came to know about the networks which are not directly connected to them. But let's look at what the distance vector algorithm does. Every router periodically broadcasts all the entries in its routing table to all its interfaces or neighbors. Okay, here we are taking a very simple topology where R1 is having two interfaces only. But supposing you had, more interfaces on R1, then every interface you will advertise every, all the entries in your routing table. Okay, and this is done periodically. This broadcast consists of a vector of distances. So you give the network ID and the distance to it from you, right? And what is the distance? That is the cost that we have here, right? So that is the cost we have here. This is what is called as the distance, right? So a directly connected network is at a cost or distance of 1 from any machine. And if you are, one hop away, so we have basically here an example of a network, which is an undirected, unweighted graph, right? So when you have an unweighted graph, you assume that the cost of every edge is 1. You have to keep this in mind. We'll see how it works and how it is used in the next slide. Now, every router updates its routing table using the information in the messages received from its neighbors. Okay, how does it update? What are the rules for updating? We'll be seeing. And the next hop information, remember that we have to fill the gateway information, right? Here we have to fill the gateway information when we learn about any network which is not directly connected to us. So how do we get that? The neighbor which is advertising the information and which we are learning from that neighbor, so that neighbor becomes the gateway. And so the broadcasting messages are used for learning additional network information as well as populating the gateway information. So once, over time, when all the routers keep advertising in this fashion, every router in the network comes to know about every network in the world. So that's basically the basic working of the distance vector algorithm. Any questions on that?
Ma'am,
Yeah.
ma'am, regarding the calculation of cost, ma'am, is it the cost from the individual node to the router, or it's the cost to the node which is being broadcasted to? So, when R2 is broadcasting its information, is the
Right.
cost of N2 advertised as 1, or is it the cost from R1 to N2?
No. R2 simply advertises information in its own routing table. All right. So here are the rules, right? When do you add anything and so on is basically given by these rules of the distance vector algorithm. Okay. Add if the entry for that network ID does not exist in the routing table, right? It's a new network that you are learning. You don't know how to reach this network. Somebody is telling you, look, I can reach this network. Therefore, you add the entry in your own routing table. And the cost is calculated how? The cost in the message, right? HC stands for hop cost of entry in message plus 1, because this is an unweighted graph. If it is a weighted graph, then you simply say the cost in the message plus the weight of the edge will give you the cost to that network from you. Okay, so if you see here, what is happening, R1 is advertising its routing table entries to R2, right? It's what are the network IDs, N0 and N1, and distances to them are 1 each. Those are the only entries in the routing table, so it advertises all of its routing table to R2. Let's go to the next slide. So what happens in response to this? R2, is using its first rule, which says if there is a new network ID which we are not aware of, then we simply add it, right? So the N0 entry is added, and if you notice, the cost is 2, because R1 advertised with cost 1. This is an unweighted graph, so the assumption is that the edge weight is 1. So you get the cost 2, and then you have N1.R1 advertising this information. Therefore, the gateway is filled with that information, N1.R1. And you are receiving this advertisement on ETH0 interface. Therefore, the interface is ETH0. So that is how it fills the the most important fields that we are looking at, right? So that's what happens. Can we go to the previous, but 2 slides previous? Yeah. Okay. So let's look at the second rule. The second rule says, if and only if you add the entry or update the entry, if and only if the cost to the network ID that you have received now is strictly less than the cost you already have in the routing table. Okay. So the entry cost is calculated as before. You have the entry in the message, you add 1 to that cost. If you already have this entry in your routing table, do not update it. Actually, that should not be added. It's an update. Update if and only if the cost is strictly less than the cost you already have in your routing table. Can we go back again 2 slides down? 2 slides forward, 2 slides forward. Yeah. Okay. So now if you see, the router R1 is also advertising network N1, right? So when you add 1 to the cost advertised, you get the cost of N1 to be 2. But you already know N1 in R2, and the cost of N1 in R2 is 1. Whereas the cost if you go through R1 is 2. Therefore, it doesn't make sense to use it. You're trying to find the shortest path, right? So N1 is not updated because of that, right? This is, the application of the second rule of distance vector algorithm, right? Okay, let's move forward to the next slide. Now, when R2 advertises its routing table, please note that it is advertising N0 to also to R1, right? But obviously R1 is not going to update N0. It is not going to update N1, but it finds N2 is a network ID, it doesn't know. So using rule 1, it adds the entry in its routing table. The cost is 2. Who is advertising it? N1.R2. On which interface did you receive this advertisement? You received it on ETH1, therefore the interface is ETH1. So now at this point, both routers know all the networks that are there in our very small world, right? You're done. This is the convergence that we talked about, that the network, all routers in the network come to know about all networks, okay? And they have a perfectly correct information about the network world, okay? Any questions? I think Bharadwaj, soon we'll be running out of time, right?
There are 5 minutes. 5 minutes left.
Okay, I wanted to start a stopwatch today, actually. Okay, so any questions on what we have done, how it works? It's a question of simply advertising the networks and the distances and using these routes. Okay, let's move forward if there are no questions. Yes.
Suppose we have so some part of the network that's down. It's taken out of the network. So
Right. So the next slide talks about that. Next slide. Yeah. What happened here? The problem is that R1 has lost its connection to N0. Okay. It lost its connection to N0 either because the interface, the network interface card of R1 which connects to N0 went bad, cable went bad, all sorts of different things that we talked about yesterday. The switch port went bad. Anything could have happened, but whatever it is, R1 has lost connection to the network N0. So what does it do? It removes the entry N0 from its routing table, right? It removes its entry from the routing table. Now you get an advertisement from R2, okay? Where you are getting N11, N21, and N02 as the advertisement. What happens? Based on the rules you have seen so far, what happens?
R1 takes N02.
R1 takes N02, right? It says N0 is reachable through R2 with cost 3 now, because the N0 is advertised with cost 2 by R2, so you get cost 3 from R1. What's the interface? Interface will be ETH1. Okay, so that's exactly what you see here, right? Instead of the no entry in routing table of R1, you are seeing N0 with cost 3, gateway as N1.R2 and interface as ETH1. Now, R1 will advertise its routing table to R2. Okay, what is it advertising? N11, N22, and N03. What will happen now? This is where the third rule, which we haven't discussed, comes into picture. Can we, essentially, what does it say? It says that if the same neighbor advertises the same network, but with a different cost. Now R1 is advertising N0 now to R2. So the same neighbor N1.R1 is advertising the same network N0, but with a different cost. You have to update your routing table. So the routing table entry in R2 now becomes N0 cost 4. Okay. Instead of cost 2, it will become cost 4. And what's going to happen? In future, R2 will again advertise this to R1. R1 will update its cost to 5. When it advertises back to R2, R2 will, update its cost to 6. R2 will advertise again. R1 will update it to 7, and so on. So this is how a routing loop is formed in the distance vector algorithm. This is called as the count to infinity problem. Okay. The infinity in the distance vector algorithm is set to, in the RIP protocol to 16. So until the cost reaches 16, they'll be doing this. And when they reach the cost 16, they'll declare that the network is unreachable. Until then, the packets will be looping bit from R1 to R2, R2 to R1. Okay. This is what is called as the count to infinity problem. What I want you people to do is try to think. We'll be breaking now, right? We'll be taking a break of 10 minutes. Try to think, what are the solutions to this count to infinity problem? What do you think we can do to prevent it from happening? Okay, and we'll discuss those in the next session.